Modern software engineering is caught in a structural tug-of-war. Businesses demand code to be written and deployed at exponential speeds, but legacy testing architectures require sequential, time-consuming validation. To understand this bottleneck, we have to look at how the software development lifecycle was built in the early 1980s. Code was treated like a physical manufacturing process. Development followed a strict waterfall sequence, where quality assurance was the final phase before physical distribution. This concentrated structural risk into the final days of a project. Teams spent months writing isolated components, only to execute a big bang integration at the end. If a core architectural flaw existed, it remained hidden until the entire system was assembled. In 1981, software engineer Barry Boehm quantified the financial impact of this delayed feedback, establishing what remains the economic axiom of the industry. This chart shows Boehm's curve. It illustrates a simple rule. The cost to remediate a software defect rises exponentially as a project progresses through its lifecycle. In the 1980s, fixing a bug after release was up to 100 times more expensive than catching it during the design phase. Today, continuous integration pipelines have compressed that ratio to around 5-to-1. Even with modern tooling flattening the curve, the underlying mathematics hold true. Catching a flaw at the source remains the most cost-effective rule in software engineering. Solving for speed requires moving from linear batch processing to continuous motion. This is the exact mechanism driving the shift-left strategy. It dictates moving quality controls to the earliest possible moments in the development lifecycle. Shift-left moves beyond merely running tests earlier. It requires designing the system so defects cannot logically form. This forces the test analyst to evolve. They move from being a passive bug hunter who reacts to finished code to an active Specification Challenger who interrogates the logic before code is even written. They intervene during Sprint Zero, auditing business requirements to eliminate ambiguities and highlight destructive edge cases. If an e-commerce product manager requests a 20% bulk discount, the test analyst immediately asks, "Does this logic stack with an active flash sale?" Answering that question on a whiteboard prevents developers from writing thousands of lines of dead-end code. In a sequential model, the analyst grades the exam after the fact. In an agile, shift-left environment, the analyst defines the boundaries of the system so the developer cannot fail. Quality becomes an architectural filter designed to block logical flaws from ever entering the codebase. Once coding begins, the primary bottleneck to early verification is infrastructure. A microservice often relies on external APIs or databases that simply aren't built yet. Engineers bypass this by building a test harness. By writing lightweight code constructs known as stubs and drivers, they wrap around the logic they are building. This enables service virtualization. The team generates a localized, simulated version of every external dependency the code will eventually interact with. Using a technique called mocking, a developer can send a request to a simulated mock server, receiving a predictable response instantly. They can now iterate locally, throwing endless variations of data at their component without touching a true production environment. The engineering requirement is absolute. Logic must be verifiable the exact moment it is written, long before system integration. Organizations implementing this immediate feedback loop routinely eliminate between 75 and 85% of their downstream defect remediation costs. Virtualization severs the temporal dependency that historically forced engineers to wait until the end of a cycle to know if their code actually worked. When the local code is ready, the developer submits it via a pull request to merge with the main branch. This triggers the automated safety net. The first gate in the continuous integration pipeline is static analysis. Before the code is even compiled, scanning tools tear through the text to find structural flaws. They flag memory leaks, null pointer dereferences, and severe security vulnerabilities instantly. This operates on a strict quality gate policy. If the automated analysis detects a critical flaw, the system structurally blocks the code from merging. If the code passes, it hits the second gate, automated component testing. Pipelines typically enforce an 80% coverage rule. If the new commit lacks enough test scripts to prove its own stability, the pull request is automatically rejected. What used to take a QA department weeks of manual checking now executes in minutes. This capitalizes on the developer's cognitive context. When a test fails 2 minutes after submission, the developer fixes the logic while the specific architecture is still perfectly clear in their mind. The CI gates replace subjective human review with mathematical certainty, ensuring the main branch remains stable at all times. Historically, checking non-functional requirements like system performance required an environment that precisely mirrored the complexity of production. Waiting until all services are linked makes identifying the root cause of a database lock or memory bottleneck technically opaque. The variables are too entangled. To solve this, engineering teams employ script-based tools like K6 and Gatling, built specifically for the shift-left phase. Instead of testing the whole system, these tools run inside the CI pipeline, isolating a single microservice API to bombard it with localized traffic. This establishes baseline testing. Teams catch performance regressions at the component level, blocking a slow service before it cascades across the network. Heavy, inefficient database queries are identified and optimized while the feature is still being drafted. This is the fail-fast philosophy applied directly to system reliability. Shifting performance testing to the left isolates components, preventing the most expensive and damaging class of production outages, the interconnected bottleneck. In the legacy era of Big Bang releases, software ended up in physical boxes on a conveyor belt. Code was a static artifact. If a defect made it onto those disks, the 100-to-1 cost multiplier became a reality through physical recall and redistribution. Quality assurance had to be a final blockade. Continuous integration erased the physical box, replacing the linear path with an infinite loop. Release is simply the first step of the next iteration. To maintain this loop, teams rely on a 3-tier architectural stack. Test-driven development ensures the logic is sound. Acceptance test-driven development proves the business goals are met. And behavior-driven development dictates how the system acts. BDD utilizes a plain text syntax called gherkin. It translates business intent into direct given, when, then statements, serving as living documentation that perfectly mirrors the actual code. However, writing UI-specific details, like clicking a specific pixel or button, directly into these feature files breaks the framework. The syntax must describe system behavior, not brittle interface mechanics. With these structures in place, software engineering abandons the static release. Quality becomes a continuous state of validation across the entire lifecycle. The feedback loop requires a mechanism for self-correction. After every release, the team holds a sprint retrospective to evaluate the shift-left strategy itself. Using the 4 Ls framework, teams map out exactly what they loved, what they learned, what resources they lacked, and the processes they longed for. If a defect leaked into production, the retrospective acts as a debug mode for the team. They trace the failure back to the pipeline, finding out exactly why the automated gates failed to catch it. Once the gap is patched with a new automated regression test, that script joins the permanent heartbeat of the pipeline, ensuring that exact failure never happens again. Moving the focus to the left allows engineering teams to ship code multiple times a day, backed by mathematical confidence rather than manual guesswork. The modern quality engineer operates as an architect of prevention, designing systems that block failure before it can manifest. The industry now prioritizes friction eliminated at the beginning of the cycle over defects found at the end.